Okay, so welcome everybody, and again, sorry about the technical issues. We still have a few glitches to work out here, but hopefully we could proceed now. So the introduction, and this image right there, KG, is perfect. So two big ideas of machine learning, classical machine learning, are supervised learning and unsupervised learning. And these two, despite the fact that there's also reinforcement learning, but these two have been making a lot of headway recently. And their quantum analogs have been showing quite a bit of improvements over the classical versions of them. Now, one thing to note, if we have to separate things into which is better on classical and which is better on quantum, we'll find that some machine learning algorithms are better on a classical computer, and some machine learning algorithms are better on a quantum computer. And for example, if we examine the subfield of machine learning, which is discriminative learning, basically just answering yes or no, well then that's a perfect environment for running, like say, supervised machine learning, because it's pretty easy to differentiate things in there. Everything boils down to a yes or a no. For example, is this a face? And a classical computer could do this pretty easily. It's like, yes, I could identify a face. Is it a face? Yes. Is it not a face? Very easy to do. And these types of algorithms are perfectly suited for classical computers. Why? Because classical computers perform calculations. They have well-defined inputs and outputs. Now, a quantum computer does have well-defined, well, I wouldn't say well-defined inputs and outputs. So for example, on a quantum computer, you would have, like, say, 5 times 3. Well, 5 times 3 doesn't necessarily equal to 3 times 5 in the classical realm. And so the output of a quantum computer appears to be non-deterministic, whereas a classical computer would be very deterministic. You know, you input in, input out. And when we examine the unsupervised learning branch and we get down into generative learning, well, we see that this is better for actually creating new data, okay? Whereas a classical computer would have a hard time generating new data, but a quantum computer would not have that issue. Why? Because of the randomness aspect to it. You know, classical computers, we could say, yes, they have randomness, but not really. You know, that's like a pseudo-random versus a quantum computer that does have that pure randomness associated with it. Okay, and so we could see now that it would be better to run supervised learning models on a quantum computer versus, like, say, a classical computer, because of that randomness aspect of it. And humans or computers would have a hard time drawing faces, right? Like, it would be hard for either one. But on a quantum computer, well, that wouldn't be much of an issue due to the fact that it does have that stochastic noise built into it directly. Okay? Okay, so what is supervised learning? And KG, if you can, go to the left here and click on the, hold on, keep that there. Go to the left side of Jupyter Notebook and click on the 3 lines for me, please. Yeah, to the left side. It's on the left.
Where? Yeah. Here?
No, the other side, sorry. Yeah, my left, I guess. Yeah, so if you look to the side, there's 3 lines, like 3 dot lines. Yeah, that's the one. Yeah, if you could click on that. And over here, this is basically our lesson plan. So we'll go through things. We'll go through introduction, a bit on algorithms, a bit on bits and qubits, 3 GIFs, parameterized circuits, encoding, classical GANs, quantum GANs, and we'll run an example in Qiskit for us. So yeah, so this is our table of content on the side here. And again, this is why I like Jupyter Labs so far. It's very good for presentation suite, very interactive in that sense. And this is why I designed this notebook for Jupyter Labs specifically.
Okay, this is great.
So so let's get back to unsupervised learning. So what is unsupervised learning? Well, in a clear and concise form, unsupervised learning is learning from unlabeled data without explicit supervision. Okay, and unsupervised learning operates similar to how human intuition works. Knowledge from observations, deduction, without clear guidance. It's like you're going in blind. What process would I use, right? And this is similar to how, like, say, a child would learn. And unsupervised learning is very parallel to the scientific method. It's like if you're doing research, if you're going in blind, well, what is your approach? And unsupervised learning takes a similar path to that learning process. More specifically, it's able to identify hidden patterns within the data itself and structure autonomously, meaning that it's able to create its own. This ability is invaluable in certain areas, in particular data analysis, customer segmentation, image recognition, strategic marketing, and the list goes on. And the image here shows an application of supervised learning, okay, where we would have a still image, but from that still image, we could create more than there is available. And this is what that living portrait shows us. It's like from a still, you could actually create a lot more. So imagine all the old photos that we have lying around. We could actually bring those to life with supervised learning, okay? Okay, so if we could scroll down a little here, KG, the key methods include. So for supervised learning, there's about these about four approaches that we could take to it. Principal component analysis, reducing dimensions. It helps in visualization and understanding our data. Clustering helps in I guess in some sense, grouping the data based on similarities.
Sir, you're not audible.
Yeah, I think we are not hearing you. Hello? I'm not hearing Ken. But you are hearing me, right? Deepa, you are hearing me, right?
Yes, Kelly.
Yeah.
Hello.
I think Ken is facing some network issue.
Yeah, might be.
Okay. So let me continue. Application of unsupervised learning. You can see this new sections and then medical imaging and customer personas. These are a few examples, but I think Ken is joining again.
Yes, KG.
Yeah. Let's wait for Ken to come back and then.
Oh, hello.
Yeah, Ken, now we are hearing you. Please go ahead.
Oh, okay. Sorry about that. Man, these computers, geez, it's like when you need them to work the most, it's like Murphy's Law. They always like fall apart when you need them to work the best. Anyways, okay, so continuing. So as I mentioned earlier, our focus here will be on the the generative adversarial networks. And this will be the one we'll implement in our session here today. But let's continue. So applications of unsupervised learning. Okay, so the applications come in where what unsupervised learning allows us to do is to see and visualize things that weren't really available to us in the first place. Also, there's less complexity compared to supervised learning. And some common real-world applications of these are for the news selection. So Google does employ this, medical imaging, and customer persona. Now, on the image here that we have here, this is another application of that unsupervised learning. when a generative adversarial learning algorithm has learned the underlying probability of, say, an image or to generate image, well, we could do a lot more with that image from what we started with. And this is what this example highlights, is that we could add, like, say, smiling features, make your face look younger, narrow the eyes, like all of these other features that weren't available before now become available to you through this generative adversarial learning process. Okay. And this is just one example of this. And in apps right now, you could probably do these things. There are probably plenty of apps where you could load in a few images of yourself, and it allows you to doctor them and change them quite a bit. So there are applications, and we're seeing this now, but these applications are very superficial. They're like the simplified application models. It's like these things, these generative models have far more capability than what we're highlighting here today. But again, as an introduction, this is a good place to start. Okay, so disadvantages, if you can, KG. So some of the issues that we ran into with unsupervised learning models are the lack of a ground truth. So data is often left to the interpreter, okay? Interpretation issues, we run into that as well. Like, well, what does it mean? Like what, because there's no defined borders, there's no defined rules to follow, well, we're gonna run into these issues. Sensitivity to input data. Unsupervised learning algorithms can be sensitive to the data that we put in. So if we're looking for a specific thing, then maybe we might need a population size versus a sample size if we're looking to identify underlying distributions of these. Next is optimal number of clusters, well, which is an issue, but it's not that big of an issue, but it's there. These are all disadvantages as well. Also, the higher dimensional challenges. So this comes back to a limit on classical behavior, in that as we add more and more dimensions to our data, well, what ends up happening is this basically takes a toll on the computer process in itself. It adds to the time complexity, how long it takes to provide you with an output. Also, these things will grow as well. So this is where we're seeing, okay, we have all these machine learning hardware. Well, yes, but the rooms that these machine learning hardwares are housing in are growing as well. So there's also the space complexity, but there's also the time complexity associated with it. It's like, if you want more classical computational power, well, then you need to grow the size until you have like supercomputers or rooms full of computers. So this is an issue that we'll see manifest in classical machine learning as well. It's like we'll reach these benchmarks where we'll need bigger and bigger and bigger areas to house our hardware. Okay, now in the terms of a quantum computer, well, there won't be these issues per se. Okay, these issues are strictly limited to the classical sense. Okay, so before moving on further into our GANs lesson, let's make sure we're on the same page with a touch on algorithms. Okay, so algorithms are, in simple, concise terms, a recipe. Okay. And what the image here highlights for us is we have an input, we have some implementation, and we have an output, okay? And besides just these, we also have a processing space, like, on your computer when you're running your algorithms, well, that computer takes some room as well. But also it takes time. There's some processing time, like how long does the algorithm take to process, okay? And with that, we need a way to benchmark the algorithm that runs on your computer and the algorithm that runs on a supercomputer, because your computer is completely different than mine, despite we might say, oh, they're both desktops, but I may have a better processor. I may have many more cores versus a laptop or versus the OS that I'm running. So here I'm running Fedora. You might be running Windows, and maybe I want to implement the same algorithm in Python or C++. So how then do we ensure that we have a specific benchmark to ensure that that algorithm that runs on your system is also benchmarked in a way that we take that algorithm and we run it on a quantum system, and that benchmark also applies there too. And the way we do this is through big O notation. But some important features of algorithm, and they are efficiency, correctness, and scalability. Okay, so efficiency refers to how quickly and efficient an algorithm solves a problem. You know, it's important to us. Correctness refers to the algorithm's ability to produce the correct output that we want. It's like, well, if it doesn't produce what we want, what's the point? And again, scalability. How does it scale with time? How does it scale with space? If it takes many universal years to execute this algorithm, then what's the point? If we require like a planet-size warehouse to store all the data, then what's the point? You know, so all of these factors play into our algorithm. And how we evaluate algorithmic performance, worst case, was with our big O notation. And big O notation, if you can, KG, just scroll down to highlight big O notation there. And big O notation basically describes the asymptotic behavior efficiency of our algorithms, okay? And it allows us to compare different algorithms, their growth rates, to the input size. Now, big O is specific to the worst case scenario. And me as an engineer, we always look at the worst case scenario because it gives us our baseline to build up on. It's like, I don't want any other issues. I need to know what the worst case is. So that way, this is where I could build off of. This is where I could begin my correction if I need to. I don't want any other outliers. I don't want any other variables. Just give me the worst case. And primarily for algorithmic behavior, this is the best place to focus. It's like, what is the worst case behavior of this? And so here I have a few examples highlighting some commonly used algorithms. So here we have O of 1, where O of 1 basically doesn't take any time to execute despite the size of, like, say, the array or something, up to n factorial. Now, I don't want to classify any of these algorithms as good or bad, but rather I'll classify them as what do you need them to do. So for an encryption scheme and blockchain, Bitcoin, bank, RSA, you want an algorithm that ties up your computational resource or ties up computational resource. And n factorial is the perfect one for that if you marry it with, like, say, highlighting where primes are. And this just ties up a lot of computational resource where it's like, you got to go, is prime? Is this number prime? Is this number prime? You have to check every single one of them to verify, is this prime? And so you could use prime numbers or two products of prime to give you another prime to use your encryption scheme, because it's just going to tie up whatever resource. And this is where that brute force attack comes in. It's like, okay, if I have to launch a brute force attack, how long is that going to take? Well, it's going to take many universal years to get into that encryption. And so this is a benefit of that. Okay, and if we look to the right here, we'll see the different behaviors of different algorithms. So quick sort, merge sort, their time complexity and their space complexity. Okay, how they grow in time and how they grow in size. Now, along comes quantum computers, in particular quantum algorithm, Shor's algorithm, and Grover's algorithm. And this is where the threat comes in for encryption, because now Shor's algorithm will take that n factorial and make it n. Better, if we continue to increase the number of qubits, well, then we could take that n factorial right down to the square root of n. Okay, so this is the threat that quantum computers pose, is that despite whatever encryption scheme you might have, classical encryption scheme you might have, and if it's based on some n factorial time complexity, well, it won't stand a chance against this particular algorithm. And that goes for any classical algorithms that's built on classical systems, okay? There isn't a single classical algorithm that will be able to stand up to the sheer state representation of a quantum computer, okay? And so the solution becomes, okay, well, we need
quantum encryption schemes now, okay? Because the classical won't cut it anymore. And so we need to migrate now to quantum encryption schemes. So quantum Bitcoin, quantum RSA, quantum, whatever it is. And in that process, we will have finally the holy grail of security, okay? Because then our security is guaranteed. Okay, now Grover's algorithm now takes unsorted lists. So whatever is in the database, time complexity, irrelevant to it. So it doesn't matter how big the database. If you execute a Grover algorithm to search that database, well, you could expect a result in root of n time, okay? So this is the behavior of Grover's algorithm. So this is why these two algorithms are so powerful already, despite the fact that we're only in the infantile stage of quantum computing, okay? They're already starting to challenge our encryption, our security, based on these classical encryption schemes we've highlighted. Okay, yes, thank you, KG. Please keep scrolling down. So we mentioned time complexity, and I'll just touch on it. It's the amount of time the algorithm takes to run. Our space complexity, how big of a space do we need to run our hardware? Here's one that's actually not usually highlighted in here, but the power complexity, and that's becoming an issue too. But we'll see more of, like, in the future, you'll see more of it too. It's like, oh, okay, you have those big supercomputers. How much power do they take to run their algorithms? Okay, that's going to be a problem as well, and we're going to have to begin focusing on them. So I just put it in there for good measure, for something to think about as we proceed. Okay, and quantum computers now and intractable problems. So quantum computers have the potential to solve intractable problems more efficiently compared to classical computers. They achieve this by leveraging principles from quantum mechanics, superposition, entanglement, interference. All of these gifts will help in that, to help us track that, solve intractable problems. One approach for using quantum computers to tackle intractable problems is with the quantum algorithms. And as I mentioned here, we have Shor's, we have Grover's, but there's others as well. For example, HHL, quantum algorithm for linear systems, and matrices and solving matrices is a big issue for classical computers because, again, they tie up so much resource in it. And so many things are built off of matrix and state vectors. So having the quantum analog to solve these issues is a big plus, and we have to give credit to these individuals who have, provided us with this. But again, more research is going on, so more is coming on, and we'll see more development in the future. Another important quantum algorithm is the quantum Fourier transform. And this is basically how Shor's algorithm is built. It's like it looks for patterns within our data or behaviors. And if there's any cyclical behavior, or if we could form them into cyclical behavior, then we could actually achieve pretty wild and efficient speedups. One way to identify these speedups is you have to think in terms of repetition. So when we say 1, 2, 4, 8, 16, 32, 64, well, there's a hidden repetition in these numbers. Okay, so for example, we have 1, we have 2, we have 4, we have 8, we have 16. So 16, if we reduce it to a singular number, that is 7. 32 is 5. So once we sum those numbers into individual single numbers, you'll find that there's a hidden pattern within it that cycles. Doesn't matter if you're at 1080 or whatever it is. If it's a base 2, there's a hidden pattern within it. Okay, and so we'll see more algorithms being developed in the future. We'll see more, well, I guess in some sense, more quantum development coming that will challenge a lot of classical ideas that we had. And this is the roadmap here for IBM's quantum development. And if you could scroll down, KG, to just give me that image. Yeah, okay. So Shor's algorithm basically, to challenge our encryption schemes right now, to break our encryption, well, that would require about 2,000 qubits. Now, according to IBM, 2,000 qubits is about near 24, 25. Okay, and if we want Shor's algorithm to go from the lowest n factorial to the lowest poly time of, like, say, root n, then we'll require a lot more qubits. And here at 100,000 qubits, well, we could see that happening in 2026. So if your encryption scheme is still based on archaic classical algorithms, encryption schemes, well, by 2026, your algorithms, your classical encryption schemes, including Bitcoin or any CBDCs, like any of these central digital or whatever it is that requires classical encryption, well, these things are about to disappear entirely, okay, made invalid. And this too is a problem for Silicon Valley and San Francisco, in that if these companies aren't ready to join on to the quantum bandwagon, well, they'll find themselves turning into sand very quickly. It's like, okay, all the silicon, okay, well, we don't need it anymore. Okay, well, you guys are useless now. And where have we seen this before? Well, we saw this development in the automobile industry, where Detroit was this massive booming industrial thing, the Silicon Valley of automobiles. And look at it now, it's like this rundown rust belt that they call it. It's like everything's turned into rust there. Why? Because I guess they failed to see the future development. Okay. So let's scroll down to our next section, qubits and bits, and make sure we're on the same page there. Oh, too far down. Chapter 3, KG. Oh, there we go. There, I don't know what happened there, but sure. Okay. So what is a bit? Now, you guys have heard this many, many times, and you've probably not answered it many, many times. But here, I'll give you the perspective from a quantum computer type. A bit is a one-dimensional movement, okay? It's up or it's down. And to switch, we do a 180. But that is a bit at its simplest form. It's a one-dimensional movement, okay? We're either up or we're down. If we had to take the eigenvalue of that bit, well, it would either be +1 or -1. Doesn't matter how long that vector is. It's either +1 or -1. It's either up or down. And the comparison here we could see between a bit and a qubit. Okay, a qubit is many dimensions versus a bit that's one dimension, one singular dimension. And so we could see a bit is just a subset of a qubit. So a qubit in this representation here, in this three-dimensional representation, is this vector that moves in 3D. It's not just bounded by 180 degrees, but rather it has access to that entire space, that Hilbert space, that three-dimensional Hilbert space. And every point on that surface is a unique representation. Okay, and the advantage here in terms of computational representation is how we could represent information. We could store the entire amount or the entire universal information. How would I say that? All of the information in the universe can be stored on a single qubit. Okay, this is the richness of that space versus a bit that will only give you 1 or 0. The entire universal representation of information can be stored on a single qubit. Okay, now the drawback here is, okay, quantum computer, I ask, what is the meaning of life, existence, and everything? And I would expect a very deep and in-depth response. Well, that is not the case. What ends up happening is, despite the fact I could store all the information of the universe on this single qubit, well, when I take a measurement, it's just going to give me back an answer of yes or no. Okay, so if I ask what is the meaning to life, existence, and everything, well, it's just going to give me an answer yes or no. And in that sense, for such a deep philosophical question, it's like, well, what's the point? You know, yes or no, that's not good enough. So if we want more richness, then we need more qubits. We need many, many more qubits. And then we could get a very intuitive, understanding answer from that. And next to the qubit here, I have this E8 lattice. And this E8 lattice, what it does is, or what it says is, all of the information in the universe, all of the electrons, all of the atoms that make up our universe, all of the forces, well, all of this could be simplified into a simple theory of everything. And what this entails is, how does a single electron communicate with every other electron in the universe? And that is like a complexity that we can't even begin to comprehend. But in the world of a quantum computer, that should be something that is very easy to understand. Okay, in terms of molecular quantum theory and wave functions, well, electron interaction is basically what defines a molecule. And so if we understand how every electron communicates with every other electron in that molecule, then we could basically work with that molecule. We could understand its lowest energy state. We could understand how this molecule itself stretches, or basically the entire behavior of a molecule could be understood. And this would give us insight into how to control, how to basically efficiently bring these molecules together to form, like, for example, okay, here. For example, this is the example I was going for. Ammonia, okay? Producing ammonia requires at least 10% of our global energy output. Okay, 10% of our global energy output goes to the production of ammonia nitrate. What is it? It's fertilizer. Okay, it's our food. It's where our food, it's what helps produce our food. Okay, now organisms, microbes, are able to produce ammonia very easily using quantum mechanics. They're molecules, so they behave quantumly. Or sorry, not molecules, organisms, so they behave quantumly. So if we're able to identify or understand how that molecule behaves, then we could basically replicate that behavior in a lab and say, okay, well, we don't need all this energy to produce it. We only need this much, and we could do it at room temperature and gain like huge amounts anyway. So this is the example I was going for. Okay, so let's move on. Classical gates and quantum gates. So just like a bit being a one-dimensional movement, well, quantum or classical circuits are themselves just a single gate, but connected in many ways, a variety of ways, to produce these 6 gates that we're familiar with in the classical sense. But when we look into an AND gate, or we look inside an OR gate, well, what we find is transistors that are acting as switches. Okay, yes or no. Okay, a one-dimensional behavior of things. It's like a yes or a no. And when we connect these in tandem in different ways, well, then we could create things like an AND gates or OR gates. But they are just a single gate. Okay, the inverter. What's another word for the inverter? The NOT. What's another word for the NOT? Well, the quantum analog is the X gate. So all of classical computers only operate on one gate, the X gate. It's either up or it's down. That's all you're doing. You're just turning on or off bits. And if we compare that to quantum gates, well, then we could see the richness that's associated with our quantum gates. Okay, we don't just have yes or no gates, but we have other gates. We have the Y gates. We have the Z gates. We have the H gate, the superposition gate. We have gates that entangle more than one, more than one qubits. Okay, so the plethora of gates in the quantum system is much richer than, say, the classical system. And so that adds to our information representation, our information manipulation, as compared to the classical systems. Okay, so again, highlighting the advantages of quantum computers. Okay, chapter 4, KG, please. Okay, so 3 gifts from quantum computer or quantum mechanics. Okay, so quantum mechanics, basically the underlying mathematics that govern the behavior of quantum computers, has provided us with 3 amazing gifts. Okay, they are superposition for one, and let's examine the image there, KG. Could you scroll down a little to center the image? Yes, thank you. So superposition is the ability of the qubit to be not just 1 or 0, but rather everything in between. In some way, I could almost say that it's a 3-positional representation. It's like yes, no, and everything else in between. Okay, and the way you could think about this in our world here is you have the North Pole, you have the South Pole, and you have the equatorial band. Well, you could be at the North Pole, you could be at the South Pole, and you could be on that equatorial band either in Africa, the Pacific Ocean, South America. That entire equatorial band is available to you in superposition. And a general concept is my face, my hand on my face, or my face, my hand, and my hand on my face. Okay, so this is one way to represent that in the general concept, but all of these states are viable states, okay? They are viable states in the sense that they are positions of our qubit. And how this plays out, or the benefit of that, is if we have a maze and we're looking for a solution to that maze to get out of that maze, well, in a quantum computer with quantum parallelism, well, we explore the entire maze simultaneously, okay, in parallel. And so in parallel, we're able to examine every nook and cranny of it until we find the solution that we want. And all of this is done instantaneously. And where we'll see this is through, like, say, Amazon packaging, where we have to find the optimal route, where we have to find where there are many options available and we want to find the best one. Okay, so this is one of the gifts from quantum mechanics. Okay, let's scroll down a little more, KG, to entanglement. Now, yeah, so this one here, Einstein couldn't wrap his head around it. Despite his genius, despite all of his understanding, he could not wrap his head around this idea. And his term for it was spooky action at a distance. So what is it? Well, when we entangle 2 qubits and we separate them over some distance, it doesn't matter what that distance is, those 2 qubits are able to communicate with each other, despite the fact that they're some distance apart. Okay, and this is that spooky action at a distance. Now, it's been theorized that to explore black holes, we would need to entangle qubits and send one set of the entangled qubits into the black hole and keep one at home. And from that, we could extract telemetry from the black hole. In the movie, Christopher Nolan movie, Interstellar, one of their issues was they could not, their mathematics wasn't rich enough. Hello? Oh, all good? Everyone can hear me okay?
Yeah.
Oh, perfect.
Yes,
okay.
I am hearing you. Yeah.
Okay. So
Go ahead.
one of the issues with them was they could not, their mathematics would fail at the black hole. It's like their mathematics couldn't represent what was in that black hole. That singularity could not be mapped, right? And so what ended up happening was, well, we have to just go through it and wing it and see what happens. But in real world, one solution would be to send entangled qubits into the black hole and then have it relay information back by communicating with the qubits here. And I left a link here on entangled qubits to be used to probe black holes if you guys want to read further on there. But another aspect is with our secure communication. This is where our secure communication will be. So we have here on the left all of the possible entangled forms of our qubits, and they vary quite a bit, but all it says is when we have 2 qubits, we could communicate with, when we have a qubit, we could communicate with the other qubit wherever it is via this spooky action at a distance. And with that understanding now, we've basically created a communication protocol called the BB84 communication protocol that uses something similar. And despite that, we also have quantum teleportation that also arises from that entanglement. So when maybe we have, say, like maybe a gigaqubit that could basically represent all the electrons on our body, well, who knows? Maybe we could actually teleport a human being to Mars and beyond. Another advantage would be superluminal communication, where we're able to communicate instantly despite the fact that we are many, many thousands of light years away, where in relativity, our communication, the electromagnetic wave would basically take thousands possibly of years to get to Earth. But with superluminal communication, we could communicate instantly. You know, you could be on the other side of the galaxy and still call up, have my meeting here today. Just a hypothetical, right? Because we wouldn't be bounded by that time, space-time issue. Okay, next is interference. So if you could scroll down, KG, to interference. So interference basically uses constructive and destructive wave behavior to either provide us with the answer that we want or nullify the results that we don't want. And if we examine the center image here, well, we have three waves in there, the red and blue. And when the red and blue are in phase, well, the black wave sums them together and produces the standing wave. When they are out of phase, they cancel and we get a zero. And just looking at that wave, we could see how constructive and destructive interference plays off. Now, this is how Grover's algorithm operates, okay? And how to interpret this is with this example here. So let's say we have a bag and we have 8 marbles in there. And one of these marbles is a yellow marble. What Grover's algorithm says is with 100% certainty, I could reach into that bag and I could pull out the yellow marble, the marble that I want, okay? Now, I could put that marble back into the bag and reach in again and pull out that marble, okay? And I could do that many, many times, ensuring that with 100% certainty, I will pull out the marble that I want. Now, this is beyond comprehension in the classical sense because it almost seems like it violates the axioms of probability theory, but not at all. How this works is like this. When we reach into the bag, okay, and we're not looking either, like the bag is sealed, we're just sticking our hands in there and we're pulling out our marble. How this works is our yellow marble is assigned a negative probability, but our probabilities have to sum to 1. So that means the other probabilities within that, the other marbles, well, their existence needs to be minimized somehow. And our yellow marble, its existence needs to be maximized somehow. So what this means is we need to make our yellow marble bigger and we need to make all the other marbles that we don't want smaller. Okay, and through this iterative process, that's what we're doing. We're taking our tiny marble and we're going to turn it into the size of a golf ball, and then we're going to turn it into the size of a soccer ball. We're going to turn it into the size of a basketball, while also the other marbles, they're getting smaller and smaller and smaller until like they're atom size. And so whenever we reach into the bag, well, it's the only marble we could grab anyway. And so this is what it does. Now, again, the bag size doesn't change any of these, but this is just a way to explain what is happening here. Okay, and that's how Grover's algorithm operates. It's like whatever's in the database, it could find it. It doesn't need to sort through it. It doesn't have to go first have to organize into linked lists or whatever else, whatever structures that we need. It does it automatically. Okay, if it's in there, it will find it. Okay, so these are the 3 gifts of quantum mechanics, and they add an aid to the capabilities of our quantum system. Okay, let's go to chapter 5. Parameterized circuits. So parameterized circuits is one of these fundamental ideas in quantum computers. And the idea of a parameterized quantum circuit is we have some variable that we're able to tune. We have some variable that we're able to change in our circuit. Okay, and that variable that we're able to tune means that we could optimize. Okay, we could offload it onto a classical computer, have it tune it, identify the parameters that we want, take those parameters, upload it into our quantum circuit, and repeat the process again. Okay, and there are many names for this parameterized quantum circuit. We could call them parameterized trial states, variational forms, ansatz, but the gist of it is it's a tune-in parameter that we have available. Now, the word ansatz we'll see appear in quite often. It appears, and at least we should know what it is. And an ansatz just means a placeholder of a circuit. So a circuit that is going to be our best guess. It doesn't necessarily mean that this is the circuit that we're going to choose, but it helps us identify a start-in position, okay? And that's what an ansatz is. It's like, okay, our start-in position circuit, we're going to start here with this. And based on the results, well, then we could tune things, change things, or make things however we see fit. And these parameterized circuits come in a few forms. And we could have the gate representation where we actually see the individual gates and the entanglement. We could also represent that entire gate representation form as a matrix. Okay, so that matrix would mean like it's the entire gate layout here, but just as numbers. Okay, the other form is the unitary block. Okay, and sometimes it's just easier to have everything in a unitary block as to just keep things simple. But most times, for simplicity, we'll go with the unitary block representation. But you could always go in and see what's inside it. Okay. So parameterized quantum circuit properties. There are a few things that we want from our parameterized circuits. Okay. And if you could scroll down for me, KG, to expressibility. Perfect. Yeah, right here. So one of the things we want from our parameterized quantum circuit is expressibility, okay? And if you look at the image here, at the top we have low expressibility and high expressibility. So the idle circuit here has an extremely low expressibility. It's not used in the space. It's not used in the Hilbert space fully. Whereas circuit A here has some expressibility, but again, it's not fully utilized in the space. It's just along the equatorial band. Circuit B is much, much better, but we have this dark spots here, these concentrations along the ket plus and the ket minus. And we don't want such concentrations, okay? We want things to be totally homogeneous throughout the system to provide us with a rich exploration space, okay? And finally, we have the arbitrary unitary, which means that we have access to the entire space, okay? Every dot on there is a quantum state. And this is what we want for our parameterized quantum circuit, is that we need that expressibility. We need that rich environment to work with. And we could actually, we could ignore the bottom definitions, but they just give our KL divergence, and we'll see what that means later in that. But this is what's important. We want high expressibility. And we could see here to the other gift here as this qubit is spinning, we could see how expressive it is. It's like, this is what we want. We want to utilize the entire space. We don't want to just be concentrated in one particular area. Okay. Next, the entanglement capability. So if you could scroll down, perfect, KG, thank you. We want entanglement. Why do we want entanglement? Well, entanglement gives us access to that space as well, but in a different form. When a circuit isn't entangled, well, that means it could be represented classically very easily. Okay, there's no advantage. We're not really employing quantum advantage in there. It's like, oh, okay, well, I could just run this on a classical system. But when we do add entanglement, well, what that gives us is it's able to correlate different components together. So women and shoes are one of these things. And they like shoes and they like bags, and those two things are entangled together. So if you're running some sort of customer profile. You want to identify women's shopping abilities with purses. Well, not necessarily women, but we'll just say purses and shoes. Well, these two things are completely different. But if we add entanglement to it, then we could see the relationship between these two things. Okay, the purse and the shoes. And so if you have to target a customer with that, you could say, hey, these two things go perfect together based on correlation. And this is what entanglement from a quantum computer allows us to do. It allows for other correlation that can't be seen from a classical perspective anywhere, okay? Only available to quantum computers. And a note on entanglement capabilities. So the QPU qubit map here, this shows the arrangements of the qubit on the quantum processor. And looking at it, we could see that 0, 0, 6, 15, and I think that's 9. Those two things are not in any way connected with each other. Okay, they have to go through the other qubits here. So when we're designing our circuit, we have to be aware of what qubits are connected to each other. Okay, because if we attempt to entangle these two qubits, well, then we'll see that they're not really physically connected in the first place. And so any entanglement that we attempt to do with them, well, they'll just be null and voided. And so when we're designing, we have to be aware of that, that physical form of our quantum processor. Okay, so entanglement provides us, or Qiskit provides us with many entanglement options, and they include linear, circular, full, and shifted circular, pairwise, reverse linear. Well, all of these have their own entanglement form, and these are just options for us to optimize our solutions. So let's say we're close to a solution, but we're not really, but we're still some distance away, or we still need to reduce our cost, whatever it might be. Well, then we might try a different entanglement scheme. Okay, instead of linear, we might try circular and might iterate through it to see which one provides us with the best results. Okay, and these are the automatic entanglement, but with the entanglement mapper, we could specify our own. Okay, we could be like, okay, well, I only want 0 and 1, 1, 2, 2, 0, or whatever. We could say this is what we want based on the configurations of the quantum processor. Okay, and the example below here, the map ZZ, just shows us one of these, how like our options in there through its own parameters. By parameters, I mean like the actual definition in programming terms. So here we have entanglement is equal to linear, and we could always change it. Entanglement is equal to circular, or whatever we want. Okay, and we'll see that later. Okay, so let's go to constructing parameterized circuits. Yeah, okay, so how do we construct these parameterized circuits? Well, we'd have to call in our methods, parameter, and we would call in parameter prefix. So parameter is for individual assignments versus parameter vector, sorry, I should have said parameter vector. Parameter vector allows us to set up a list of parameters. And again, it's pretty straightforward stuff. I just put in a bunch of demo images here just to show, like, you know, the parameterization as the placeholder. And if you could scroll down just to show the circuit that's created there, KG. Yeah, that's good, perfect. And this would be the results. Now, you guys could always play around with this and see how it works and, you know, get an idea of how parameterized circuits work. But let's move on. So encoding. So encoding is taking our classical data and making it quantum data. And this process is extremely important. You know, going from classical data to quantum data. And there's a whole process involved in that. This isn't an issue in terms of classical machine learning where there's no state preparation, there's no encoding process. We could just take our classical data, run it through a machine learning algorithm, classical machine learning algorithm, and we get a prediction out. In the quantum sense, we have to take that classical data, encode it, then run it through our machine learning algorithm, then get a readout, and then make a prediction on that. Okay, and so that entire block in there is the state preparation, the unitary evolution, meaning that as how our state moves through that circuit. And finally, we need to take a measurement on that and then make sense of it and probably hand it over to a classical optimizer. Okay, and these steps, or what we need to consider, I've listed here as 1, 2, 3, up to 5, these 5 points. So how it's represented, so quantum state representation, the data loading, quantum algorithm essentials, like what do we need, how we need, like what algorithms are we implementing here, basically. The algorithm complexity. Does the encoding process grow exponentially, taking away any quantum advantage, or does it not? There are techniques to minimize that, and there's a few techniques to do that. And performance factors, you know, like our precision, how much noise there was, or is there noise? What type of outcomes do we have? Like all of these considerations we have to add in to our decision-making process. And let's go to the next section, choosing an encoding scheme. Okay, so choosing an encoding scheme. Well, there are a few encoding methods that we need, but each one has its own advantages and has its own disadvantages in more ways than one. And for example, basis encoding. So basis encoding, classical data is mapped to computational basis states of a quantum system. So we take our classical data and we map it to the basis states. The basis states are the 0 and the 1. Oh, 1 second. Yeah. And it has its own advantage. It's straightforward to implement, very easy. But the limitations are it's not very efficient in terms of representing that space, you know, utilizing that Hilbert space that we have to work with. Okay. The next encoding scheme is amplitude encoding. If you could scroll down, KG, to amplitude. So amplitude encoding represents complex data distribution. And the way it does this is it encodes our information into the amplitudes of our state vector. And again, pretty straightforward. For example, x1, x2, x3 here, 6, -12, 11, 7. We first need to normalize those, get our normalization, which is 19.12. And we take that and use that now as the amplitude vector. And basically, this is just all there is to amplitude encoding. And again, it has its advantages, it has its disadvantages. Advantages, it's more efficient than our basis encoding. But limitations, it could be a little more complex to implement. Okay, next, angle encoding. So angle encoding is probably by far one of the best encoding schemes, as in it utilizes the space much more efficiently. Also called higher encoding, it represents classical data by encoding it to the relative angles between the quantum states. And we could see this here with our cos xi and sin xi. Now, this definition here is the state vector representation, the state vector, how we would define the state vector in its form. And what's missing here is the theta over 2 factor, where we have to divide that value over 2 to make up for the special unitaries and special orthogonal states. But again, all that not that relevant. So what's important is to understand that when we encode with the angle encoding scheme, it's a much richer environment, and it allows us to utilize the space much more efficiently. Yes, so we're able to exploit the Hilbert space much better. The advantages here is we're using the phases. We're using the phase and we're using the amplitude as well. So it's like it's wrapping up both basis encoding and amplitude encoding into one form. And we could see here how we tensor product the other values as well. So we'd take like the state vector definition of the first qubit and tensor product it with the second qubit and so on and so on. And it's, again, just a much richer environment. And we'll see that comparison later. A derivative of angle encoding is dense angle encoding. And if you could scroll down to dense angle encoding there, KG. And dense angle encoding just means we're using our the relative phase as another parameter to store as well. So not only are we using the cos and the sine, but we're also using the relative phase. And comparison of encoding schemes, we could see now the differences between these and why angle encoding is much richer. You know, and thank you. So we could see the comparison here. Okay, we could see basis encoding, amplitude encoding, and angle encoding, and how they use the Hilbert space much more efficiently. Okay, so let's move on now. Chapter 7. Are we making good time? Hopefully. Okay. So back to our lesson. Now that we're all on the same page, we understand the advantages that quantum computers present us, and we're ready to move on and get into the meat of things. So let's go now. Classical GANs. GANs are special. Why are they special? Well, because they're able to create something new. Now, a little caveat on there is that despite the fact, or classical computers aren't random. And so when we say they're able to create new data, well, that new data is bounded by that pseudo randomness. And with a high enough representation, we'll eventually start to see repetitions. But for now, we'll just say, yes, they're that good, and they're able to create this new data, okay? And through this adversarial form of this data generation, we are even able to extract other features that weren't possible before. And so the way to understand the classical GANs is like this. So we have somebody generating these images that are on the screen right now. Okay. Now us, the viewer, we're the discriminators. Okay. Yes, we're pretty familiar with that term now. So we are discriminating these photos. And by discrimination, what we're saying is which of these photos are real and which of them are fake. Okay. Now, some of them are real and some of them are fake. Now, if you as the discriminator chooses a real one, or says a real one is a fake one, or a fake one is a real one, well, that just shows that now they're so good, the generator is so good, that you're unable to tell the difference in any of these photos. And so if you now, as the participants, are able to take a look at this image and tell which one's real and which one's not, well, then that's pretty good. Now, unfortunately here, they're all fake. So that just shows how good our discriminator is, our generator is. Okay, so how does it work? How it works is like this. So let's say we have a population size of cats, okay? We have a population size of cats, meaning that we have all the cats in the world, or cat images in the world, and that is now our population. Now, from that population, we want to take all the house cats out of that. Okay, we're going to take all the house cats out of that population, and that's going to become our real sample. So if you look here, we'll see real samples. So house cats are now the real samples. Everything else that's rejected, we could use that as our latent space. okay? We need to start somewhere. So we're going to use that now as our latent space. So jaguars, lions, tigers, anything that's not a house cat, we're going to throw it into our latent space. Who knows? There might be a dog in there too, but we'll throw it all in there. So we have our real samples and we have the latent space, which is basically just the noise, the thing we don't want. And so now we're going to feed that noise into the generator. And our generator is tuned to say, okay, you need to create images of a cat. Well, a cat has whiskers, it has these cat eyes, tiny ears, and blah, 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 blah. Now, mathematically, how we represent that is with a distribution. It's like, oh, well, a cat has this particular type of distribution. Okay, so your job is to mimic that distribution. Okay, so the generator now creates this image of what it thinks is a cat, sends it to the discriminator, and the discriminator is now, which it knows what a cat is, it's like, oh yeah, I know what a cat is. The discriminator will then say, well, that's not a cat, or that is a cat. In the case it says that's not a cat, well then that output is fed into a classical optimizer to identify the costs associated with both the discriminator and the generator. And the classical optimizer comes back and it says, good job discriminator, generator, you're terrible, try again. And so it repeats that process. Generator updates, passes it to the discriminator. The discriminator is like, still not a cat. Goes to the classical optimizer. Optimizer's like, good job, discriminator. Bad job, generator. You're bad, bad, bad. You need to do better. And so now, between the generator and the discriminator, there's this adversarial action taking place. It's like, oh, how am I going to fool this guy? How am I going to fool this discriminator? You know, I got to create better images. I got to create better fakes. And so through this optimized loop, these two things, discriminator and generator, become better and better at detecting fakes and generating fakes, okay? Up until we reach a point, that point known as the Nash equilibrium, where the generator's like, I can't tell the difference. Maybe it's a fake, maybe it's not. I can't tell anymore, okay? It can't. And so we reach this Nash equilibrium that tells us, okay, there we've reached the plateau. The generator is very good at creating these images of house cats, and the discriminator can't tell the difference between the samples that it has and the new fake ones that it's created. Okay, so fake, generator, real, discriminator. And that will be our parameters that we'll use from here on. Okay, and if we could scroll down now, KG. And what this adversarial network has allowed us to do now, KG, if you could scroll down. Yes, right here. Let's get Ryan Gosling now. And so this is where that image came in for Ryan Gosling, that we're able to alter this. It's through this generative adversarial relationship. This is what allows that type of reproduction. Okay, now the equations here, or the functions that govern this relationship between generator and discriminator, is like this. So B here represents the adversarial relationship between the generator and the discriminator as a min-max function. Now, this is the quantum GANs definition, and I pulled it up here because it will be relevant later, but just to show how simple it is. So, reading it now, we have minimum, theta g, that we're trying to minimize, and theta d that we're trying to maximize. And so that definition goes as the probability of, oh, hold on, KG. Yeah, could you scroll back up? Yeah, right, yes, right here. So we're going through the quantum GANs definition here. Okay, so theta g, theta d, min max is equal to the probability of d with theta d, the real, and that is our real vector. This is how we define it, plus the probability of d theta d g theta as our fake. So the way to read this is discriminator real versus discriminator generator equals fake. Okay, and we'll see these D's and G's play out later. Now, in the classical GANs, well, that's a little more complex to define. It's like the min of G and the max of D is equal to the loss of DG, where these are functions. And we have EX here as the expectation of X with the probability of R of X of the log. Yes. So I left this all in here for you guys to work through and for you to actually see the definition. But in the classical case, we have the Z factor here. And in the quantum case, there is no Z factor in there anywhere. Okay, the Z factor has to do with the noise that we have to input into the classical state. But we have none of that in the quantum case. Why? Because quantum is already stochastic. It has its own noise, and it doesn't need it in that sense. Now, we'll see, it might need it if we want to narrow things, put bounds on our creativity, but in general sense, we don't need it. And D here, so we have A, B, C, D, so simplified classical GANs definition. We could reduce it to a form like this if we try to remove the noise factor out of it. Yes. So this is the simplified GANs definition, where it's like the expectation value of the log dx plus the expectation value of x of log of 1 minus dx. And simplified, it just says these two probabilities must sum to 1. So the probability of log dx plus the probability of log 1 minus dx must sum to 1. So if log dx is 0.4, then guess what? Log of 1 minus dx has to be 0.6. So that way everything sums to 1. Okay. Now at times we'll have like other unknowns in here, like say for z. So if we have log dx is 4 or 0.4, and then we may have a noise vector of like 0.1, and then our log 1 minus dx might be 0.5. But whatever it is, it has to sum to 1. We have to maintain the axioms of probability rules. Okay, so now we could jump directly to the challenges, training challenges and evaluation concerns. So if you could scroll down, challenges and limitations, perfect. So theoretical limitations. Okay, so classical computers fall short of complex tasks naturally. And the way we'll overcome this is with quantum computers, okay? And quantum computers will promise, due to their inherent randomness, state representation, like many states can be, like the representation is like just 2 to the number of qubits. So let's say 2 to 1,000. Well, that number is something ungodly already, and that's just 2,000 qubits. Our goal is like millions or billions of qubits, okay? Higher dimensional space. We have access to these higher dimensional spaces. Entanglement advantage. You know, where do you get that from a classical computer? You can't, okay? And training challenges. GANs training is delicate due to the adversarial network. It's easy to veer off and get into these rabbit holes. GANs are vulnerable to input noise. You know, there might be noise issues. GANs risk generating repetitive output. So again, because we're dealing with pseudo-randomness, well, how long is it before we actually have to go through the same repetition pattern? These are all limitations, you know, and the noise input. It's like the noise will produce these confidently incorrect solutions. The GANs will tell, the training process will be like, oh yeah, it's perfect. We're good. We're perfect. But the solution is like incorrect. And so confidently incorrect means I am sure of the I'm sure of the solution, but the solution is incorrect. Okay. And evaluation concerns, well, lack of consistent evaluation metrics, but that's the same for all GANs. It's like, where do you draw the evaluation criteria? What are the metrics of evaluation? And we'll find that there's very little to none. It's like, oh, okay, well, this is the cat I was looking for. Okay, looks like a cat. Sure, that's good enough for me. But as a baseline, there is none. It just continues. Okay, data may overfit. You know, again, that's like that that confidently incorrect situation. You know, it's unable to produce original data. And the biggest issue in terms of classical GANs is they require substantial computational power and specialized equipment. Okay, so let's move on to our quantum GANs. And quantum GANs are the quantum analog, but they're much easier to implement and more efficient. Okay, and quantum GANs merge the innovations of quantum computing and generative adversarial networks together. Quantum GANs, the generated, the discriminator, or both can operate as quantum circuits. They exploit quantum benefits like the inherited randomness, data superposition, and enhanced performances, okay? Now, one thing to note is the dynamical differences between these two things. So, intrinsic quantum probability. So we have them listed here as 1, 2, 3. So for the first one, intrinsic quantum probability, quantum mechanics naturally operates on probabilities. This native probability aligns with the discriminator's random guess and benchmark. So this is where that power is going to come from. We're not bounded by, you know, limitations in terms of pseudo, but we have random guesses. Proof simplification. We saw that earlier with their equations. It's easier to see the proof in quantum mechanics probabilistic foundation. And superposition and entanglement, well, we know the benefits of those now. So as we mentioned earlier when the lecture first started, some MLs are better on quantum computers. For example, GANS is one of those, and I've left how they're better here for you guys to touch on, you know, with the examples here. So for example, GANS facilitate faster and accurate sample generation. GANS can generate quantum keys for encryption. GANs are useful for tasks in quantum safe cryptography. Okay, and these are just a few examples here that you guys could always read through. And we have Deus Ex Machina here, me joking to say like this is where the God will emerge out of, okay, for our AI overlords. But who knows, maybe it won't be all bad for us. Okay, let's scroll down. Different approaches to GANs. So there are many approaches that we could take, but we'll only focus on a few of them. If you could scroll down for us, KG, to highlight the different approaches. Yeah, perfect. Excuse me. So based on quantum circuits, so pure quantum GANs, meaning that the generator is a quantum circuit and the discriminator is a quantum circuit. We have hybrid GANs where certain aspects of these might be classical. So the generator could be a quantum circuit and the discriminator could be a classical neural network or vice versa. We can have some integration, but these are known as hybrid GANs. And based on data, we can have continuous variable GANs, which is good for time series data analysis, or we could have discrete GANs akin to working with our qubits. The training methodologies, always the variational form. Why? Because that's how we utilize quantum computers in the near term. Is that we don't have enough qubits to really do the things we do. We'll have to wait for it. But that doesn't mean we can't start innovating right away. And the way we do this with what we have is through the variation, excuse me, the variational form. And the variational form could be implemented either on penny lane-based GANs or Qiskit-based GANs, which is what we'll do here. So what is a pure GANs? Well, it's one that's made up of quantum, 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 everything. Okay, and the objective of the full GANs is for quantum generators to reproduce a desired state psi. And GANs theory, if you could scroll down, KG. So this is an example of our encoding for the generator and the discriminator. But keep scrolling down, the quantum theory, GANs theory, the images there, please. Yeah, keep scrolling down, KG.
Is it still should go down?
Oh, no, too far down. Sorry.
Oh yeah.
Sorry.
Okay, I think
yes,
there is
go
a lag in
to
these.
GANs theory. Yeah.
Yeah, I am here in the GAN theory.
Yeah, this image right here. Perfect. Okay.
Okay, cool.
So we could see that the forms are pretty similar to the classical sense, but we're dealing with state vectors in that sense. So our real data is a state vector that will encode. Our noise is a state vector that will encode. The fake data is also a state vector, lambda here. And what the discriminator produces is also state vectors, either real or fake. And the image to the right, the NZAT, is just an example of how we'll create the generator and the discriminator and the real data encoded. And yes, so if you could scroll down now, KG, to the image below that. Yeah, perfect. So this is a more detailed representation of what's happening in the classical GANs. What it highlights here is we'll offload the discriminator's results into a binary classification run on a classical system. So this is where we'll be doing our optimization. And we'll be using TensorKira with the Atom optimizer. And when the discriminator rejects a sample, well, then this will be offloaded to the classical optimizer, and the classical optimizer will update the generator model and update the discriminator model. And this image here will follow as our template. So when we're talking about any of the specifics things here, I'll circle what it is we're talking about for the classical sense. Okay, let's go to real discriminator images now. And the real data discriminator is pretty straightforward. So we'll have some unitary representing our real data, and we're going to feed that into a unitary representing the discriminator. And notice that it's parameterized here with the theta. And we'll take some measurement out here. Now, I'll just explain this one for the real data generator, but I'll avoid it for the fake generator. So we prepared the real data through a unitary U of R such that we define data R, our state vector, is equal to some unitary times that state vector, where the tensor product here is the number of qubits that we have to work with. Okay, then we feed that unitary of real data into a parameterized discriminator U here, but it's called d theta d to highlight the fact that it is a parameterized circuit. Okay, and then we take a measurement z to arrive at the discriminator score on the real data. And so this evolutionary process is described as unitary data, theta d, into the state vector d real, tensor product with the number of qubits that we have. Okay, so it just shows how our state vector moves through up until it gets to our measurement. Okay, and moving on to fake discriminator now, fake data discriminator. Well, it's pretty much the same thing, but it's just now we're dealing with the discriminator. If you could scroll down, KG, to the fake discriminator, perfect. And again, we have here how, like I've described here through the steps 1, 2, 3, 4, what's happening. And it's basically the same thing as our real data that I described. But the components are different in that sense. Okay, so let's move on to our GANs in Qiskit, chapter 9. Okay. So GANs in Qiskit. Understand quantum generative adversarial networks with distribution. So the first thing we need to do for our demo is we need to choose a distribution. Now, a distribution to emulate, to say, okay, mimic this. And we could either have normal Gaussian distributions, a log normal distribution, a binomial distribution, or any relevant probabilistic distributions of random variables. And next, we'll encode the circuit, and then we'll run through the GANs model to understand how it's doing what it's doing. Okay, so the first step one, create the real distribution. So here we'll just import the packages that we'll need. And this is the first cell here. If you could scroll down to the second cell, KG. Yeah. And so we have a variable, oh, too high, just a little lower. Yeah, perfect. We have the real distribution here, which is equal to 3. And we have the real circuit here, which is equal to the quantum circuit that we're going to define. And so this quantum circuit is made up of 3 qubits that we specified here. And here I've chosen these gates, but again, you guys could play around with this code here. There's nothing special about this, these gates here. It's just I wanted to make something difficult, but at least challenging to the experiment here. Okay, so once we have this and we run this cell, we produce this right here. So we have the real quantum circuit, which I just mentioned earlier. We have a real state vector, which we have here. And keep scrolling down, KG. Yeah, and we have our real histogram distribution here. And so this is what we'll attempt to mimic with this circuit. So this is what we want to train our quantum GANs on to be able to mimic. Okay, and so now next step, step 2, creating the generator and the discriminator. Okay. So to create the generator and the discriminator, Qiskit offers us several auto-encoding, parameterizing, feature mapping circuits. And what these are is it combines the feature map and the NZAT here together and creates it automatically for us. Okay, and we have a few options here. We have the Z feature map, we have the ZZ feature map, poly and local, to local, and so on and so on and so on. So all of these feature maps here are limited in their own sense. They're advantageous to some and other situations they're not. But Qiskit allows us to do this automatically. And so once we have this auto-encode and parameterize and feature map and circuit, we'll just call it our variational quantum circuit. And if you could pull up that image right there, KG, to center it, variational quantum circuit. So this is the process here, is that we have our variational quantum circuit now. We're going to take a measurement. We're going to upload that to our classical optimizer, and we're going to update our parameters on our quantum system. Okay, so that's that loop there of optimization will follow. Okay, so defining the quantum generator G theta. And you could scroll down to that image. Perfect. So again, this is where we are. This is what we're going to do now, that red square. Generated examples. So scroll down into that cell block. Perfect. So we have the generator is equal to the to local, that auto-encode and parameterize and feature map and circuit. And we feed it real data distribution. So again, we're just creating a quantum circuit here. And we have parameterized single qubit rotations. Now, these are in here to just highlight the fact that you could specify your own rotations, okay? And here we have full entanglement. Like as we mentioned before, we have all sorts. And once this definition is done, we create this circuit that we see here. So this is what's inside our generator. Oh, 5 minutes left. Hey. Okay, let's try to get through it in 5 minutes. We probably can. And here we have our unitary generator block. So this is what our generator looks like. Okay, keep scrolling down. And so we've defined our generator. Now the discriminator, we're just going to use the efficient SU2, just like we did, well, similar with the generator, but the process is all the same. Okay, entanglement full, 3 qubits, and so on and so on. Okay, let's scroll down, keep going through the generator. And this is our generator circuit here. Okay, now we're going to augment these things together. We're going to put the generator and the discriminator together. Okay, so scroll down. Yeah, keep scrolling down. Okay, and so how we put our generator and our discriminator together is we're going to create a new circuit, and we're going to basically take the generator circuit, place it on there, and if you could scroll down again. And we're going to place our discriminator with it. So now we've created our generator and our discriminator, and we placed them together. Okay. Next, we're going to create the real discriminator, real and discriminator. So a real example with our discriminator. So earlier we created the generator with discriminator. Now we're creating the real with the discriminator. And the process is still the same. Yeah. And next, we're gonna append, okay, so besides, yes, so we have the real, okay, yeah, this is still the real now, perfect, so we're good here. Okay, so noise not required. And this is where we would put in our noise vector, but because we're a quantum system, we don't need noise. So with or without noise, the variational quantum generator is capable of directly modeling the wave function of interest, so long as the NZ is of adequate capacity, meaning if we've designed our NZ properly. So because quantum measurements are I can't even talk now, intrinsically stochastic, we do not need additional randomness prior to. So randomness is intrinsic to quantum system. Hence why we don't need it. Okay, generator cost function and generator cost and discriminator cost function definition. Okay, so I left this here as to explain measurements for us. And when we take a quantum measurement, what we're doing is we're looking for the lowest energy state of the system. And we do this by taking a state psi and sandwiching it with a Hamiltonian, where the Hamiltonian is the z basis that we're taking our measurement in, the orientation that we're taking our measurement in. And most times, it's the computational basis state, which is the z. So this is all we're saying here. And so the lowest energy state, E naught, has to be less than or equal to the measurement we've taken before or we're about to take prior. Okay, so obviously in a for loop, this would just be, is this the lowest value that you have? Yes or no? No, okay, make this now the lowest value and repeat the process again. Okay, that's all we're saying here. So let's go down to cost. We could scroll down past cost. We've already defined our min-max. Yeah, generator. Oh, just go up to generator cost and discriminator cost. Just scroll up a little here for us. Yeah, right here. Oh, scroll down a little. I think there's a bit of a lag in there. Yeah, scroll down a little. Yeah, perfect. So the generator cost is basically just the probability of fake true minus the probability of real true. And so we define this as the probability of DG minus the probability of DR. Okay, this is all we're saying. And it's pretty straightforward. And if we go to the generator now, if you could scroll down, KG. What we're saying here now for the generator is the cost of the generator is just the negative probability of fake true. And this definition here is basically what we've implemented in our code cell down here. If you could scroll down to the code cell. Yeah, and so we define the generator here. And if you look, you'll find the cost of each one. But let's scroll down to something more important. Let's scroll down to the KL divergence. Right here is fine. So the KL divergence allows us to compare two different distributions, okay? And so when those two distributions are the same, then our KL divergence goes to 0. And when they diverge, well, then you could see how our KL divergence, or it diverges away from 0, okay? And so this is what is going to allow us to optimize to say where we started with our real distribution and the generated distribution. And so this is how we're going to optimize them to show like they are coming together. And this is that metric that we're going to use, is the KL divergence. And I've left enough here for you guys to go through. And if we could go through now, scroll down to 7. Yeah, keep going. We've defined this. So this is just the code cell for that. But now we instantiate. So 7 here is we're instantiating our quantum neural network. And as we mentioned earlier. So if you could scroll down now to that code cell. So in that code cell, we're defining our quantum circuit, our QNN. So we're just going to pass it our generator distribution. Yes, our generated circuit and our discriminator fake circuit. So we're just defining our quantum neural networks here with our generator and our discriminator. And for 8, yeah, you could go ahead and highlight that just to make sure that we're all on the same page here. Okay. And so for 8, this is where our classical optimization loop is going to be implemented. And we're going to use the atom, the first one there, to do that optimization for us. And so now if we could go to 9, our starting distribution. And so 9 this is where we start. This is now what we're going to upload to the generator to begin with. So as you can see, we no longer have parameters in here, the theta, but we actually have values in here. And if you could scroll down now. Okay, so this is our initial generator distribution. And if you could scroll down just a little more, I just want to compare, this is what we want. So the one above was the one we're starting with, but this is what we want. And now let's go to 10. This is where we begin our training. Now, I would have liked to have gone through this, but it's a little involved. So this is just where we train things. And yeah, let's go beyond that. Let's go to, yeah. Oh, keep scrolling down. Yeah, keep scrolling down. Yeah, keep going down. Yeah, right here. Yeah, this is perfect. Yeah, or just the data that's coming out of this. Okay, so once we run that training code block here, it's going to produce something like this, where we keep track of the epochs, the generator costs, the discriminator costs, and the KL divergence. And this is the read-in. So if we run this, but I don't know, if, KG, if you have all the packages loaded, I would say don't run it now. We might just get stuck in there somewhere. But this would be the results that we would have here. And if you keep scrolling down beyond that, and so here, I explain how to interpret the generator discriminator loss graph. So I tell you what to look out for here, but keep going beyond that. And here we have our understanding the KL divergence graph. So how to interpret it. And finally, let's get to our results. Yeah, and here's our results. And here, basically, we could see now how the discriminator, or how the generator and discriminator losses interplay with each other. And for interpretation, I left some explanation as to how to interpret these graphs. But more importantly, what we could see here from the KL divergence is that our two distributions, what we started with and what we generated, as the training progresses, we could see that it goes down to 0. Okay, it starts off at 0.8, probably goes to 0.9, but then it begins to slowly slow proceed down to converge to 0. Okay. And if you could scroll down now, and now we could see our trained generator distribution versus our real distribution. And this is very good. This is very impressive right here. Like beyond impressive, this is almost scary in some sense because it just highlights the potential that quantum generative adversarial networks will have, okay? And as you could see here, it has mimicked our real distribution very closely. So say if that real distribution was an encrypted key, well then our trained generator could mimic it very easily. Okay, it could say us, okay, well, key 1 was 000, key 2 was 001, key 3 was 10, like you guys get the idea. But very easy and at least very scary at the same time. And conclusion. You're welcome. So we went through quite a bit. Sorry, I had to rush things through here, but quantum generative adversarial networks can potentially process and generate complex data with fewer resources than classical GANs can. They offer advantages of leveraging quantum superposition and entanglement to model intricate data distributions very efficiently, okay? And their efficiencies are highlighted as can produce complex data using fewer resources, modeling, naturally suited for simulations and modeling quantum systems, whereas a classical computers will fall short of all of these things. It has entanglement advantages. All of these gifts that we mentioned from quantum mechanics can be implemented here, and this is where it draws its strengths from. And as we progress, as you see that IBM development roadmap, it will become better and better at approximation up until we just leave the classical world altogether. You know, and we should see some major breakthroughs coming up in the next few years with that. And thank you very much. I'm sorry about the initial issues. You know, Murphy's Law, technology will fail you when you need it the most.
That is an amazing session, Ken. Ken, I need your permission to share this Jupyter notebook with attendees who are interested. I know many of the people who joined here personally. I know Surya Sai, Sayanthan, Nalini Madam, and I don't want to miss anyone. And our Andrews Tal. And this is amazing for all those who are staying till the delay. I will invite Uma Deepa to deliver the vote of thanks.
Okay, sure thing. Yes, absolutely. Go ahead. It was created specifically for you and for this training session.
Thanks a lot, Ken. Appreciate it.
Sir, I have few questions. Can I ask?
Yes, absolutely.
Yeah, please.
Sir, yeah, thank you, Ken. The wonderful session. We learned a lot. I have a few doubts. Can you give me some applications of Grover's algorithm in database, related to database?
Oh, okay. So Grover's algorithm can be implemented for database, or in fact, unsorted database, okay? So unsorted database means that you haven't optimized the database. You haven't organized things. You haven't done anything. So if the database is just unsorted, then implementing the Grover algorithm in there will provide you with huge speed ups in terms of search. Okay. And we could also do this just not for data in like a database, but what about images? You know, what if I'm looking for a specific image profile and I know it's in the database? Well, then Grover's algorithm can be implemented here. Now, the limiting factor here is the number of qubits. Okay. Grover's algorithm can be probably implemented for like maybe, I don't know, like very small items that you want to search for. So you could create your own, say, database, and you could implement the Grover's algorithm within it as well. But if you're looking for literature, there's plenty. Just search up Grover's algorithm and a whole plethora will show up explaining and implementing the ideas of Grover. Now, why we're not seeing major applications here is just a limiting factor, just the number of qubits. You know, this is the only limiting factor. But the proof of concept is there.
And I have one more question for qGAN, means quantum GAN. Which SDK is best, whether Qiskit or Pennyline?
Okay, because I've worked on Qiskit so much, I'm pretty familiar with the API, so I choose to go with Qiskit. But that's just a matter of preference. You know, Pennyline does do a few things better, but I like to work with non-vaporware type of implementations. And by vaporware, what I'm saying is a lot of companies out there profess to have all this quantum capability, but can I access it? Can I actually implement code on it? Can I work with the actual hardware and get results off of it? And the answer is no. Okay, a lot of them you can't. And so I am biased towards the one where I can actually tangibly work with it. And so that's Qiskit and IBM's quantum computers right now. You know, I don't want to take, like, my work requires more proof than proof of concept. We require actual physical hardware access. And so I tend to work with that and bias towards that specifically.
Okay. And see, in this work, we are not discussing about the performance of this work, no? How to measure the performance of this work?
Yes. So there's no metrics that we have that we could put down and say, okay, well, this quantum GANs is going to take this much longer, or this classical GANs is going to take that long. There is no base metrics yet. Everything is just a matter of identifying with, like, you know, one's eyes or based on the data results, right? Now, I can't say for sure that in the future that won't be the case. You know, maybe we will have that, but one area that we do attempt to benchmark is in loading the classical data into a quantum system. And quantum systems are, well, now becoming much more efficient at loading the data. Before, we would have exponential losses just from the fact that we attempt to load so much classical data that it takes away from the advantages that quantum would provide. But through these different techniques, we're regaining back that efficiency and those benefits. And it doesn't matter how big your circuit is. Most times, it takes the same amount of time to execute. So we could see now that your circuit could be very, very big, but the runtime is the same as a very big circuit versus a very small circuit. And this is one of the benchmarks we're starting to see now.
Okay, sir. Can you please suggest some reference materials for this one, this title? Which one you referred?
Yeah. Okay. You know what? I left out a lot. Okay. Where is it? In there somewhere. I think, yeah, I guess I should have left some references. Okay, this is what I'm going to do. I'm going to send you guys a message, an email of some very good references that you could distribute to whoever would like it.
You share to Deepa.
Thank you, sir.
Deepa will share to the community. And
okay, no
Deepa
problem.
knows Nalini madam, so she will touch. Thank you.
Thank you so much, sir.
Oh, you're welcome. Thank you, guys. Sorry about the issues. I'm starting to lose faith in these computer setups now, but thank you, KG. You're a wonderful, excellent moderator. Thank you very much.
Thanks a lot. Sabari, do you have a question?
Oh, somebody.
Sabari Krishnan. Yeah, go ahead, Sabari.
Thank you. Thank you, Ken, for the wonderful talk here. So I have one question: that how do you overcome the errors in the quantum circuit? Because this one is a 3 quantum bit circuit. I'm not sure about the depth of it, but let's say it's a bigger circuit. How can we overcome the errors?
Okay, so the errors are still there. The errors are omnipresent, and errors as in decoherence and noise they will be something that will continue to manifest in the near future. But what we've seen so far is you can reduce these errors and you can reduce the effects of noise. In particular, you can reduce the effects of deep depth circuits to achieve the barren plateau. We can mitigate some of these by how we load the data, okay? And the data loading aspect appears to be where most of our issues and our bottlenecks are. It's like taking that quantum data, taking that classical data and moving it into the quantum realm. And it does make sense in that sense. Why? Because a qubit of 1,000,000, right? The state representation there is impossible on a classical computer. So how then does a classical computer interpret the results from 1,000,000 qubits? Well, it can't. Okay, what we need to do is we need to truncate the results in chunks and then feed it back to the classical system so that way it could represent it. But even then, we'll run into limitations on memory. So it appears this is going to be an issue of loading a bottleneck where we need to load data into the classical system, and a problem where we need to unload the data off of a quantum system. Sorry, yes. And these errors are going to persist until we find a better way to do it, to say, okay, we could take the quantum data and somehow interpret it without a classical system. Well, I don't know of any other. Yeah, it's almost virtually impossible to say that how exactly we're going to do this, but who knows? Maybe we'll need to connect it directly to our brains with a quantum sensor, because the classical computers won't work. There's no way for it to represent such large amounts of information from a quantum system. So the future is bright, and the number of qubits that are coming down, definitely. One thing I should mention is we can use machine learning algorithms to attempt to correct for the noise on a quantum system. And we can use the quantum GANs to almost preempt the noise that we're going to see. And so these are like areas of research, but they're viable areas of research to see how we could control the noise. Thank you.
Thank you, Ken. And one more question maybe, can you briefly tell me like how you actually update the parameters, because this is how you are actually reaching the global minimum, right? That's the true ground state.
Right. Okay. Thanks, KG. Let's see. So how we do the updating, and I've left a lot of literature here. So where's the updates? Okay, go up
The goal here is to use the binary classification system, which is a classical system we use.
Yes. Where is that? Where is that? Okay, let me see. Okay, in the code here, somewhere, like to local. Okay, if you could scroll down, perfect. So keep scrolling down, KG. Hopefully we'll get it here. Scroll down. Yep. At least past 4, 5, actually maybe even 7. So try to go to section 7 of the qGANs or of Qiskit implementation. Yeah, no. Go to 9.7.
There is instantiation.
Yes, keep scrolling down. There is code for the TensorFlow instance. Keep going down.
You want to search for
okay,
tensor?
Here, perfect. So creating the classical optimization loop, right? Okay, so in here, if you could go to that code cell that's right there, we have, this is how we initialize. So we have a initial generator parameter is equal to numpy.random.uniform distribution. So we're going to implement a uniform distribution, and we're going to set the parameters from -pi to pi. So that way we encompass the entire distribution, right? And we're going to create one for the initial discriminator as well. And now we're going to use the TensorFlow variable initialized generator prep to basically take that initial generator parameters and put it into a vector that now we could use to load the parameters for the generator and load the parameters for the discriminator. Okay, and if you keep scrolling down. Okay, yeah, right here, stop. So above we have initial generator parameter values. So these are now the initial generator parameter values that we've taken from our sample space. And we have the initial discriminator value parameters that we've taken from our sample space. And now we're going to take these values and bind them to the generator. So if you look here, the generator, we've got like actual values now, right? We don't have the theta values in here anymore.
Yes. Yes.
Yeah. So now we've loaded them into our generator as the generator parameters. And this is basically repeated. And scroll down. If you can, KG, go into training. Okay, actually go up just a little. Oh, hold on, go up a little more. I want this image and the one above it as well. Okay, scroll down a little. Yeah, keep scrolling. I want this histogram and the one below it on the same screen. If you can, perfect. Okay, so now we've created this initial histogram, right, from our random distribution. And
Yes,
this histogram is going to be compared to our histogram that we had before. So the top histogram is one we just initialized, and the bottom one here is the one we're going to compare it to make it. Okay?
Okay. Okay.
Okay. And if we scroll down a little more. Yeah. And this is the binary classification part you wanted, right? So if you could scroll down a little more, KG, for us, into the code block right here. Yeah. So this code block here basically does the optimization, does the generator the parameter updating, all in one. So I'll describe the top code block here. So quantum discriminator parameter update. Okay, you see that, right? So
Yes.
we're going to take the partial derivatives with respect to theta d here of the code block. And now we're going to upload our data. So if you look here, we have discriminator fake QNN. So we have our QNN created. We're going to use backpropagation of the generator's parameters, the discriminator's parameters, and we're going to send that to a matrix. And we want that to be in binary. B0 or 0B110. Okay, so that's just for the discriminator. Then we repeat the same process for the generator below it. And this is basically the entire training code block right here. Now, do you need me to walk you through it?
No, I understood. Like
okay.
We are doing the gradient descent using the atoms, and then we are using the cost functions here for to do that. But,
exactly. Yes, sir.
Great.
okay, thank you very much.
Yeah. Yeah. I think Deepa, you can take vote of things.
Okay, KG. Good evening, everyone. I'm not taking much of your time. On behalf of my QT team, I would like to propose a vote of thanks to our speaker, Mr. Ken, and to all our participants for attending this event. Mr. Ken, thank you for sharing your expertise with us today. Your talk was informative and engaging. We especially appreciate your insights on today's topic. We expect you soon with your next informative topic. To all our participants, thank you for taking the time to join us. We are so grateful for your support and interest in the topic. We hope today's topic was very useful and have added more knowledge to your quantum computing journey. Once again, thanks to all my team members for making this event a successful one. And I thank Mr. Ken and all my team members and the participant. See you soon for the next event. Thank you very much.
Hey, thanks for having me.
Thank you. Thanks a lot. Bye-bye.